Okay, so today's lesson is a shorter one, and I'm sure you're all happy with that, Thanksgiving weekend and all. Um, I'm going to walk you through how to build a fertilizer solution and talk a little bit about pH drift and what contributes to it. And then I'll go over the fertilizer assignment, which will be up and I've updated it, and that will be due before your break week. So basically, you come back, write your midterm, and then we move on to the second half of the course. So, man, time flies, eh? Anyways, okay, so this process of me walking you through the steps will help you figure out how to build the fertilizer solution that's in the assignment on that spreadsheet. So on the assignment, there's targets, the Weller and Veerman targets for cucumbers. Forget their names, whatever. And so you start with calcium nitrate. Okay, so what we do, we've got our calcium nitrate on the tab of the spreadsheet, and we know what the millimole target is. So what we want to do is we want to look at, to start with, our calcium level. Now, typically, you would also look at the calcium level in your water and then subtract that from this because you don't need to go beyond. But let's just assume there's nothing in the water and we need so many millimoles of calcium, so you're going to add that many in the spreadsheet. So if it says, 1 millimole calcium nitrate, then you're going to put a 1 on the input side. The spreadsheet's at the end of the lesson. I'll review that again, but okay, so you start with the calcium component of your fertilizer target, and you put that in under calcium nitrate, okay? Then you move on to MKP, or monopotassium phosphate. And again, it's the phosphorus that we're actually looking at target-wise, not the potassium, just like it was the calcium in the calcium nitrate that we started with. Okay, do you see kind of where we're going? We're picking off the lesser nutrients first using some of the key ingredients, and we'll probably go back and adjust it, right? So we add our MKP to hit our phosphorus target. I don't know what that is. Let's say it's 1 millimole or 1.5 millimole. So you're going to add 1 to 1.5 or whatever it is, the target for phosphorus of MKP, all right? Now, remember, this is just a reminder that phosphates go into the calcium tank. Traditionally, I call that tank B, but it doesn't really matter. Whichever tank has calcium is separate. Oh, geez, I got that wrong, didn't I? It goes separate from the calcium. Easy to make a mistake on that, isn't it? Because remember, calcium reacts with phosphates to form an insoluble salt. Okay. Next, we want to go to our potassium. So we started with calcium targets, tried to hit them. We moved on to phosphorus targets, tried to hit them. Now we're going to use potassium nitrate to hit our potassium target. Okay, so you go to your spreadsheet, you start inputting millimoles for your potassium target. Maybe your potassium target is 5 millimoles. So you're going to add 5 millimoles of potassium nitrate and see where that takes you. If in the process you exceed, this is just a universal approach, not necessarily every nutrient, but if you happen to exceed your nitrate millimolar output by adding the potassium requirements to get to your potassium level, you can stop and switch from potassium nitrate to potassium sulfate to get more potassium without overshooting your nitrate level. Again, this is because plants can tolerate fairly high sulfate levels. Now, which tank does the potassium sulfate go in? It goes opposite calcium. Okay? So, if you still need more nitrate, let's say you added your potassium nitrate, right, to hit your potassium target, and you've got your potassium target locked in, but you happen to need more nitrate, then what you do is you would oversupply calcium nitrate because plants can handle a little excess calcium. It's not that bad. As long as your ratio between calcium and magnesium doesn't go way out of whack, which would be hard to do. then you're good to go. So then you would go right back to the very beginning here and add a little more calcium nitrate. So you might overshoot your calcium target slightly, but you'll get your nitrate target, which is important because nitrate is the biggest contributor to plant growth. Lastly, you hit your magnesium target, right? So you're going to add your Epsom salts. And that goes into the sulfate tank, which is not calcium, right? And then, of course, after that, there's micronutrients. Obviously, at the college, we use a premix, but, you know, super cheap farmers will independently measure each individual micronutrient. And this is just reminding you of some of the subtleties between the different chelating agents. DPTA has the broadest pH range. It's also the most expensive. Actually, no, EDDHA costs the most, but DPTA is pretty good. So you'll see that one a lot. And I mentioned this before, EDTA is toxic in certain levels. You have to be watching you don't get, it starts accumulating in your hydroponic tanks, because things might look fine for a while, then they start to go downhill. And that's because as the plants are using the micronutrients, they're discarding the EDTA, and those EDTA levels are building up in your nutrient solution. So EDDHA is the best, DPTA is second best, EDTA is the least. And typically we put the micronutrients in the sulfate tank away from calcium, because some micronutrients are actually sulfate salts. So it's best just to be safe and keep them away from calcium. All right. Skip those parts. Okay, so looking at the spreadsheet off to the right-hand side, you'll see a column that says MEQ per liter. That stands for milliequivalents per liter. And what that's doing is it's tallying the charges of the various ingredients to see how they balance up. Oftentimes they should balance because the salts dissociate equally. You know, potassium and nitrate split into equal amounts of charge. But some of them, it's less equal. So remember the difference between how we name these? Positive is cats have pause, so it's cation, and anions are negative, the opposite. So essentially, it's tallying the cations and anions in the solution to see if they're balanced. If they're balanced, we would have zero pH drift, which eventually it's not perfectly balanced, and so pH sort of tips one way or the other. It's like balancing a broom. You can get pretty good, but it's always kind of wanting to lean one way or the other. I'll explain on another slide a little more clearly how that looks. Another thing that's useful about milliequivalents is that there's a simple multiplication factor of 0.055, which converts the MEQs to an EC value. So if you were actually mixing up your nutrients and dumping them all into a tank to be used completely as a nutrient solution, you could check your EC and it would confirm that you got your measurements right, because it would be pretty close to the predicted EC value, assuming you haven't got too much coming from your city water to begin with, right? So you subtract that, obviously. Anyways, that's what that is. Sometimes people ask me, I don't go on about it, but that's the milliequivalents. In this particular slide here, what it's showing basically is on this column, we have our positive charge, our cations, and on this side, we have our anions. And looking at them, you'll see, and this is probably more commonly the case, there's slightly more cations, and it's primarily because of the ammonium that is contaminating calcium nitrate. And because there's slightly more positive charge in the fertilizer than negative, what happens is, remember, when plants are absorbing nutrients, they try to maintain a neutral charge. So if they're absorbing a positive ammonium, they're going to release a proton. And protons contribute to acid. So what happens is this solution over here, if it was in your nutrient tank, the pH would slowly go down as the roots are feeding. Now it's important, the only reason it happens is because the roots have to be feeding, because as they absorb, they would acidify the nutrient solution. Whereas if we reverse it, this is just reminding you, ammonium, which is a cation, when it's absorbed, the root produces a proton, which makes the pH drop. If you're absorbing a nitrate, the root produces hydroxyl, which increases the pH. So if we look at this example here, where we have no ammonium, we've managed to scrub all the ammonium out, right? So there's an excess of negative charges or anions, which means that the nutrient solution is going to drift towards higher pH. All right, so a slow rise in pH will happen in this context. So like I said, sometimes it's really hard to balance that out. Often there's contaminants in the water which throw this off. The idea is you have it as close as possible. Most farms have automated pH and acid injection to keep an eye on things to make sure the pH is correct. So typically nutrient solutions tend to drift towards a rise in pH, which requires addition of acid. All right, regarding the fertilizer assignment, okay, that's up on Blackboard under the assignments tab. The objective for this assignment is to learn how the various chemical inputs will dissociate and contribute different nutrients. So for example, potassium nitrate, we know that when we put a 1 millimole of potassium nitrate in the left column, it's going to produce 1 millimole of potassium and 1 millimole of nitrate. And all as you go down the list, you see how those things dissociate and interact when you're building a fertilizer. So the idea is you enter the millimole targets. Actually, I've entered them already in the spreadsheet to make your life easy. They're at the top. Make sure you look at that because that's what your targets will be. They're the Wellerman-Verwer targets. And follow the sequence that I discussed today, right? So starting with calcium nitrate to hit your calcium targets and then so on. And build your fertilizer solution. And then if you go down to the bottom of the spreadsheet, there's a notes section. It's important that you fill that out for my marking to be able to give you the marks because I have a rubric for this. I just want you to make a note. It doesn't have to be an essay. Just a couple of sentences is fine. To indicate where you had maybe some minor difficulties and your strategy or compromise to hit the targets as closely as possible. Right, so just like in the lesson, I had, maybe you had to switch to potassium sulfate because you didn't want to overshoot your nitrates, whatever. As long as it makes sense and logical, I'll give you full marks. I think I've said there is no perfect answer necessarily. There's many different ways. You can be slightly higher and lower in others. As long as you're not way out of whack, you should be good to go with a decent mark. Okay, and then submit it under Blackboard under the assignments. You just attach your spreadsheet and hit submit, and then away you go. This is all due before you go away on your break week, so that way you can focus on studying for your midterm when you get back, and all the list of questions I'll give you, and should be good to go. All right, I hope you have a great Thanksgiving weekend, and if you want some entertainment, look up William Shatner's video on how to safely fry a turkey in a deep fryer. Now, mind you, I'm not American. I don't deep fry turkey. And between you and me, I'll tell you, I'm not really a big turkey fan. I find it's always dry. Maybe it's how we cook it. We usually get ham. So anyways, hope you guys have a great weekend and stay healthy. All right, bye. Oh, yeah, geez, I already said goodbye, and here's the spreadsheet. It's like a postlude. Haha, you thought I was done, but I'm not. Yeah, this is the spreadsheet, right? So the targets, I've already put them in the spreadsheet at the top. There's your 12.25 millimole of nitrate, 1.25 of phosphate, 2 millimole of sulfate, 6.5 millimole potassium, 7 millimoles calcium, and 2 millimoles magnesium. And the idea is you're just going to enter your values over here in the respective chemicals, right? And they're going to spit out into the various sections. Remember, there's an ammonium contaminant with calcium nitrate. They're going to spit the values out, and you'll see the output millimoles down here. And then you want to compare with what your target was. Right? Compare with your target. Compare with your target. And then make the necessary adjustments. So again, follow the sequence in the lesson today, and that should make this fairly straightforward. So This is where you're putting your inputs. This is the only place where you're putting your inputs. The milli equivalence, if you're curious, is off to the side here, and the notes is directly down below, okay? That's it. Now I can say goodbye and have a great Thanksgiving weekend. All right, bye.